So section 4.3 talks about, among other things, conditional probabilities. And we'll define it this way. Probability of A given B, and that's what this thing is read as, is given. The probability that event A occurs given that event B has occurred. So that little orange line there really reflects the fact that you're telling somebody, all right, we know that event B has occurred. I want you to calculate the probability that event A occurs. So we're going to start with example C from our handout. So it's called the denomination effect, and I'm going to just recopy that table down here. So let's see, let's go to example C. And it's going to start with an experiment that was done with some college students. They were either given 4 quarters or given a dollar bill, and then it was observed if they purchased some gum or kept the money. So I'm just going to call it purchased or kept. But let's take a look at these different possibilities and write out our table. Given 4 quarters, given a dollar, and then purchased or kept. So let's just take a look at some different possibilities here. And give ourselves a neat looking table. Whoops. I was wondering if either of you was going to be a hero or heroine. Thank you. I could just imagine both of you guys looking at each other. All right. Let's throw in some values here. Thank you. So we have 27 people who were given 4 quarters and purchased some gum. And 16 people who kept the money, who were also given 4 quarters. Amongst the people who were given a dollar, 12 of them bought gum, and 34 of them kept the money. So let's fill in some marginal totals here to help our calculations out a little bit. So the first marginal total I want is over here. That's going to be 43 who were given quarters and 46 who weren't, were given a dollar, for a total of 89 people here. Now it's not a bad double check of your work to see that the marginal totals work in this other direction as well. So I got 39 here and 50 here. So it's 89 both ways. That's good to see. It's reassuring. We're going to start out with a simple calculation, and that is the probability that somebody spent the money. On average, what's the probability amongst all the people in here that they spent the money? So this is A, probability of that they spent the money. Keep in mind that probabilities are between 0 and 1, so don't give me just 89 or 39 or something like that. What's the overall probability that they spent the money? I think I heard somebody whisper 39 over 89. Yep, 39 over 89. Nice. So that's about 43, 44%. Okay. But now we're going to change things up. And when we start working with conditional probabilities, what you're doing is you're effectively changing the sample space. Oops, wrong way. So I want to look at the probability that they spent the money given that they received 4 quarters. So am I looking at all 89 of these individuals anymore? No, I'm not. I'm looking at a smaller set of this table. So in fact, what part of this table am I going to be looking at if I'm looking at the people who received the 4 quarters?
43.
Yeah, just the 43. So given that they received 4 quarters, I'm going to be looking at this part of the table right there. And of those who got 4 quarters, what's the probability that they spent it on gum?
27/43.
Yeah, thank you. 27 out of the 43 bought some gum. So about 0.6279. Okay. Did that make a difference to our probability? Does knowing that information affect the probability that somebody... But yeah. So what that's saying is that there's a relationship between these two variables, between spending your money and what kind of denomination or how your dollar was given to you. Let's try the next one. Probability that you spent the money, given that you received a dollar bill. Received a dollar bill. So again, you've got a different sample space. It's no longer just, the whole set or people who received the 4 quarters. Now we're looking at this part right here. They received a dollar. So you're limiting it. You're no longer looking at the whole table. You're looking at this part of it. Ryan, what's the probability you think that if you got a dollar bill that you spent it? Just give me the numbers. You don't have to give me a percentage. 12/46. Perfect. And that percentage turns out to be about 26%. 0.2609. So did the denomination that you got change your behavior with spending or not spending money? Yeah. So are these dependent or independent events? What do you think? Are these events related or are they completely independent?
Dependent.
Got to vote for dependent. I got to vote for independent. Well, if they're independent, then the outcome of one shouldn't affect the probability of the outcome of the other, right? So if they're independent, the fact that you receive 4 quarters shouldn't affect the probability that you spent the money, right? Is that what happened? Did the denomination that you get affect your probability of spending the money?
Yeah.
Absolutely. Overall, there was about a 44% rate of spending your money, but that rate changed dramatically depending on if you got 4 quarters or not. So these events are not independent because the outcome of one changes the probability of the other one. So these events are not independent the outcome of one, which is the denomination you're given, denomination given, changes the probability of the other one. Changes the probability of the other one. So they're not independent. It's not necessarily a really easy thing to get comfortable with and get used to. Probabilities are probably one of the more challenging aspects of this course, which is why we're spending extra time on this today and why I kind of go easy on this and testing you. Some of the big things you need from probability would be ideas like probabilities are between 0 and 1, Probabilities have a complement. And we're going to work on some counting rules in section 4.4 as well. But let's keep going. Comments or thoughts on this first one, example C? Let's move over to this one down here, example E. And I've got a couple different looks at a sample space. So there's this one right here, which is a Venn diagram, and this one right here. So what's the experiment? Well, the experiment is you're flipping two coins. So that one, here's your tree diagram. It's giving you more or less the same thing. We want to look at these and try and decide what's going on with flipping some coins. Are we going to get independent events or dependent events? Here's another definition for you of independence. Two events are independent if the outcome of one does not affect the probability of the outcome of the other. So that is something that you should kind of keep in mind as you're working through this. Let's take a look at a couple events, and I'll define them for you up here. H1 is the event of a head on the first flip. Event of a head on the first flip. And likewise, H2 is the event of a head on the second flip. So we got H1 and H2. I want to look at a couple different probabilities here. Let's start with the probability of H2. And we'll do that from our Venn diagram down here. Now I can get away with this because each of these points in the sample space is equally likely. But how many possible outcomes are there for this experiment? How many diagrammed here?
4.
4. All right, there's 4 diagrammed. How many result in a heads on the first flip? Or a heads on the second flip, I'm sorry, H2. 2. So overall, your probability of getting a head on the second flip is 1/2. Now, let's look at the second one. Can someone put into words what this is saying? What probability are you being asked to calculate? Patty? Close. Both being heads, but what's this little vertical bar here mean? Given. So in words,
The probability that your second flip is head if your first flip was already head. Right?
yeah. So given that you flipped a head on the first toss, what's the probability of getting a head on the second toss? Now what I want you to do is I want you to look at your tree diagram, which is a different way of getting at the same thing that our sample space over here, the Venn diagram is. And I want you to circle the new sample space. Because I'm telling you up front that, all right, you got a heads on that first flip. So your sample space is no longer the same thing. Just like in the last one, I said, you know what, we can circle this because our new sample space is the people that got 4 quarters. Or I could circle this. Our sample space now has been reduced to the people that got $1. So your sample space has changed. Circle your sample space on this. What's that new sample space look like? Bridget, what should I circle here?
The top one.
The top one?
Yeah.
Anything else?
Are we doing just heads being the second or heads being the second? Okay.
Well, I'm circling the given, which is heads on the first flip.
Oh. Okay, so heads on the first one would be the top two.
Yeah, there you go. So there's our new sample space corresponding to that right there. The fact that you got a heads on the first flip says, okay, this isn't happening now. We're just focused on that. All right, perfect, thank you. Joy, you want to try the next? See, you looked up at the wrong time. You caught my attention. So, yeah, it's all right. It's all right. You got a nice visual diagram here. How many possibilities are there in our new sample space? Two. Yeah, it's either this one or this one. Of those two, how many of them have a head on the second flip? One. Perfect. Perfect. So my question to you, are these events independent? I got a yes and a no. Yes. Oz says yes. Gentlemen in the back are split on that one. What has to be true if they're independent? The outcome of one doesn't affect the probability of the other one. Here's the probability of a head on the second flip. It was 1/2. If your buddy whispers to you before you flip that second head or flip that second coin and says, psst, there was a head on the first flip, does that give you a better chance of correctly calling the next one? No, because they're independent. This is like I said like a week ago or something like that when we talked about the gambler's ruin. A lot of times people will sit at the slot machine and go, oh, it's due, it's due, it's due, it's gonna hit, it's gonna hit, it's been a long time. No, the probabilities don't change. The probabilities are the same, even if it's been a long time since you got lucky and won a jackpot or something like that, or since the dice rolled 7 or not a 7. Those probabilities don't change. The dice don't have a memory chip that goes, oh, well, it's about time I came up with, boxcars or something like that. It doesn't. These are independent because the probabilities haven't changed. Unlike our last example, where the probabilities did change. All right. Why don't you look at the next one? And let me pull it up here. Let's see, that one. No. Let's see. Yeah, might be a little bit easier for you to read up here or on the handout, whatever. Let A be the event that the subject is telling the truth. B be that the polygraph test indicates that the subject is lying. Use your own words to describe the notation probability of B given A. I'm going to give you a minute to think about this and then talk to your neighbor a little bit, see what you guys think. See if we can't come up with the same letter A, B, C, or D. So again, we're going to do one of these pauses here. And if you're watching this later, then just fast forward until I remove this. All right, so now that you got your own thoughts on this one, turn to a neighbor. Do you agree with your neighbor? Are you on the same page? Or tell your neighbor why they're wrong. So one way to work on these for yourself is to just kind of write down, a brief summary of what each of these things are. A is the event that the subject is telling the truth, and B is the event that the polygraph indicates the subject is lying. So, subject, indicates the subject is lying. So, on a count of 3, 1, 2, 3, or 4, A, B, C, or D. Let's see by show of hands what you guys are thinking. 1, 2, 3. All right. Uh-oh. Yeah, that was kind of like I'll look around and see whatever. I'll do a little sample of somebody else's. And yeah, all right. 4, I agree. Probability that the polygraph indicates they're lying, which is what we have here, given that the subject is actually telling the truth. So D was our winner. So well done on that one. And let me give you one more bonus problem here. I gotta think a little bit about mnemonic notation here. So I'm gonna let B be the event that someone draws an ace of hearts from a standard deck of 52 cards. Okay. And let's let H be the event that a card drawn at random is a heart. Now, just FYI, I don't expect people to know, a standard deck of cards too well, and actually different countries have different decks. So there are 13 hearts in a standard deck. There's a couple probabilities that I want you to find, and then I want you to decide if these probabilities are independent, or these events are independent. So first of all, find the probability of B, and secondly, find the probability of B given H. Yeah, from a standard deck of cards. Then we're going to need to decide if these events are independent. But we're not looking for just an ace. We're looking for the ace of hearts. There's only one of those. Yeah, thanks for that clarification. There is one ace of hearts. Okay.
Was it right? Yeah.
If it wasn't, I would have said something.
You ain't checked my stuff all day.
And you got it right.
Okay, you should say that.
Well, I guess I just did.
You said, I'm afraid that's right.
What's the probability that somebody draws the ace of hearts out of standard deck?
1 out of 52.
1 out of 52. But if I kind of caught a look at the cards and I saw, oh, it was a heart. Now that you know that it's a heart, what's your chance of getting the ace of hearts?
1 out of 13.
There's one ace of hearts, there's 13 hearts. So your probability is 1 out of 13. Are these events independent?
Yes.
Yes? I see some disagreement here. Yes, no, yes, no. Sometimes. Sometimes? There is actually a sometimes in math, which is like maddening, but that's a different story.
I think it's because the probability that it's an ace of hearts relies on the probability of getting an ace, and vice versa. The possibility of it being an ace of hearts relies on the probability of it being a heart card,
Well,
right?
We'll take a look here. Your probability of getting the ace of hearts was 1 out of 52. Did the knowledge that the card you drew was a heart change that probability? Sam's saying no, it didn't. I don't know. These don't look the same. I think getting a heart, knowing that you've got a heart, changed your chance of getting the ace of hearts, right? I mean, it's up to you. Are you convinced by that? I mean, there's only 13 cards that are hearts, and there's only one of them that's an ace. So this probability and this probability are not the same. These are not equal. So these events, are they independent or are they dependent? Sam? Dependent, yeah. Because the outcome of this changes the probability of this. So these events are dependent. The outcome of H changes the probability of B. Yes, Lisa.
But if you're picking a card from the deck, isn't it just random?
It is random, but in the second case, you're given a little bit more information.
Right.
And that extra information changed our probability. So that extra information is somehow related to your probability of getting the ace of hearts. That means that they're dependent. Compare that to what happened in this example. Did knowing that you got ahead on the first flip give you a better chance of getting ahead on the second flip?
No.
No. So this extra information did nothing for you. It didn't change the probability.
Okay.
So these were independent, whereas over here, that extra information changes your probability. I got one last one here for you. So kind of the all-star part here. Find probability of B given H bar. Ooh, so now you got to think a little bit about H bar. What's H bar represent? One more time? Not a heart. All right. So calculate that probability now. So let's be clear about this. This is the event of drawing something that's not a heart. So it could be a club, it could be a diamond, it could be a spade, but it's just not a heart. What's that probability now for the second part? The probability of B given H bar. What's that probability?
0 out of 39.
0 out of 39, right? if you didn't draw a heart, how can you draw the ace of hearts, right? I mean, the problem is telling you, oh, you didn't draw a heart. You've got some other suit, and none of those 39 cards are a heart. So you can't get a ace of hearts given that you didn't draw at least a heart. So again, these events are dependent. Knowledge of what happened with this event changes this probability. It was 1 in 52. Here, it's 0. So that's a drastic change for sure. Those two events are dependent. Any follow-up on that one? No? Good with that last calculation? You tell me truthfully? All right. All right, let's put this one in books. And